Alright, so now we move on to the laws of electromagnetic induction. So basically there's two laws that we need to know for this chapter 21. Okay, the first law we need to know that is Faraday's law. Okay, so Faraday's law states that the strength of the induced EMF is proportional to the rate of change of magnetic flux linkage linked with the circuit. Okay, so in other words, is saying that our EMF, okay, is directly proportional to the change of magnetic flux linkage. So magnetic flux linkage, you can also put it as change in magnetic field. Yeah, actually it's almost the same, just a minor difference that you will learn when you go to higher level. Right? So magnetic flux linkage basically is you can treat it as magnetic field. Okay, so note that in order to have EMF, you need to have a change, okay, a change of your magnetic field. If there's no change, there won't be any EMF induced. Alright, okay. So of course, the strength of the induced EMF is proportional to three things. Number one is your number of turns of the coil, or the solenoid, right? So number two, strength of the magnet, and number three is the speed at which the magnet is pushed in or pulled out. Right, so let us take a look at this simulation. So this is a coil of wire connected to a voltmeter, right? So you notice that I have a magnet nearby, but the coil of wire is not showing any there's no current being induced in the coil of wire, right? Because although that is magnetic field, right? Let me show you the field meter first. Let me measure. Alright, so you'll notice that at here, don't need to look at the BXPY and the last part. Just look at the first line, 1.20. At this coil of wire, it experiences a fair bit of magnetic field, about 1.2 Gauss. Okay, but how come it does not have a induced EMF? Because there is no change in the magnetic field strength. But if I move my magnet towards the thing, okay, so you notice there's a bit of deflection, right? Okay, because there's a change in your magnetic field. So this is what I call the electromagnetic induction. Okay, so the strength of this induced EMF, whether it's high EMF or low EMF, depends on three things. First of all is the number of turns of coil, right? So now it's only 2 loops. Okay, so what if I increase? Okay, so yeah. Right. So what if I increase? Okay, so I push in at the same. Okay, so notice that there are more deflection. Okay, so another is your strength of magnet. Okay, so if my strength of magnet is huge, so you see the deflection is even more. Okay, and last but not least is the speed I push in. Okay, so if I push it very fast, the deflection is very fast. Okay, yeah, so these are the three factors that affects the strength of induced EMF. Alright, okay, so next is the Lenz's law. Lenz's law tells us the direction of our induced EMF. For Faraday's law is the strength of the induced EMF. Now is the direction. Right, because EMF not only have magnitude, also have some direction, whether it's clockwise or anti-clockwise. Alright, so Lenz's law states that when the magnetic field of a circuit changes, the current produced must act to oppose the change. So basically, the coil of wire or the coil of circuit must always oppose the change. Okay, so in this example of when I push the magnet into the coil, okay, so initially the magnet is right here. Okay, let me use this. Initially the magnet is right here, so the coil experience maybe 1.2. Okay, so initially, okay, 1.2 Gausses lah, okay, or Tesla also can. Right, so the coil of wire experience 1.2 Gausses of magnetic field. Okay, so when I push the magnet into the coil of wire, the coil of wire will experience even more magnetic field. Okay, so maybe aftermath. So it will experience maybe 5.2 Gausses of magnetic field. So there's a change of 4 Gausses of magnetic field. Okay, so what will the coil do? The coil do not like changes, right? So it will tend to oppose the change. In order to oppose the change, it must first induce an EMF. Okay, so it will induce EMF in this particular direction. Okay, if you use your right hand grip rule, this will be north, this will be south pole. Okay, why does it induce a north pole at point A? It's because the coil of wire do not want the magnet to come in. Okay, so you want to repel the magnet. Alright, so that's why it will induce EMF in such a direction that my point A will be north and point B will be south. Alright. Okay, so what about if the magnet is not moving? So I put my magnet near the so-called solenoid. Okay, so initially, the coil of wire experience only 1 point maybe 4 because it's nearer 4 Gausses of magnetic field. Okay, since it's not moving, right, after some time it still experiences 4 Gausses of magnetic field strength. Okay, so you can see that there's no change. The change in magnetic field is equal to 0. But for case 1, the change of magnetic field is about 4. Okay, because 5.2 minus 1.2 is 4. Okay, so since there's no change, right, there will not be any induced EMF. Right? Okay, so last but not least, I'm moving my coil, my so-called magnet away from the coil. Okay, so since initially if I experience this coil experience initial experience magnetic field strength of maybe 4. Okay, 4 Tesla. I think let's put Tesla better. Alright, after that, since I move the magnet away, the coil of wire will experience lesser magnetic field. Okay, so it's about maybe 2 Tesla. Okay, so you can see that there's a change of magnetic field strength of 2 minus 4. So it's always after minus initial, right? Yeah, so it's equal to negative 2 Tesla. So there's a decrease in your magnetic field. So what will the coil do? Because the coil don't want this change. Okay, so the coil wants the magnet be inside of the coil itself. Okay, so it will tend to attract back. He want to attract back the magnet from going away. Okay, he don't want the magnet to move away. Okay, so he will attract back the magnet by inducing point A as south pole and point B as north pole. Okay, because south and north will attract, right? Yeah. Okay, so before you create a magnetic poles, north and south, you need to first induce a EMF. So the induced EMF will flow in such a direction. Okay, yeah, use your right hand grip rule, you notice that your thumb is pointing towards the so-called left, right? Okay, so yeah, so your point B will be north and point A will be south. Yeah, so that's how the coil will want to oppose the change, right? Okay, so this is linearly, so it's a straight line, right? Okay, what if I have another different scenario where the magnet is dropped vertically? Okay, so same thing, the idea is the same. Alright, so when the magnet drop into the coil, case this point 1, okay, yeah, so the coil of wire, okay, will experience more magnetic field, right? Because initially maybe it's just here. Okay, so here is your north, of course here will be south. Okay, so initially the coil of wire maybe experience only 4 Tesla. Okay, after you drop it, the coil of wire will experience even greater magnetic field, right? Because it's nearer. Okay, so there's right here maybe experience from 4 Tesla to 7 Tesla. Okay, so there's a change of positive 3 Tesla. Okay, so final minus initial. Yeah. So it will induce an EMF to oppose this increase in your so-called magnetic field by this point will be north pole and this point will be south pole. Okay, yeah. So it will flow the current. If you use your right hand grip rule, right, it will flow anti-clockwise. Okay, so it will flow like this. So this is the current, flow of current, right? Okay. So okay, then after that, when the magnet is inside the coil, it will not have any change of magnetic field momentarily, just for a short while only. That's why there's no induced EMF for case number 2 or point B. Okay, after that, when the magnet come out of the coil, because the coil initially experienced maybe 10 Tesla inside, when the magnet is inside the coil, okay, 10 Tesla. When it come out, right, the magnetic field strength definitely decrease to maybe 5 Tesla. Okay, so the coil of wire do not want this decrease, right, because there's a decrease of 5 minus 10, which is minus 5 Tesla. Okay, so the coil want to attract back the magnet by inducing a north pole right here and south pole right here. Okay, so if you use a right hand grip rule, the current will flow in this direction, in the so-called clockwise direction. Okay, so this is clockwise, this is anti-clockwise direction. Okay, so you notice that the induced current for case number 1 and case number 3, right, they are flowing in opposite direction. All right, okay. So you look at this EMF graph. Okay, so when the magnet just goes in, okay, the induced EMF will be in this particular direction. So this is the positive part. Okay, so this will be your anti-clockwise direction. Okay, anti-clockwise. Okay, at point B, it will have no induced EMF momentarily, just for a very, very short while, maybe 10 to the negative 9 seconds. Then after that, when it comes out, the current will flow in the clockwise direction. Okay, so this is clockwise. Right. Okay, and notice that beside the direction changes, right? So how do they indicate the direction changes? By putting your curve on the top and at the bottom, right? So when the magnet comes out, it will go in this direction. Okay, and notice one more thing is that your EMF at point A and point C, point A is lower than point C in terms of magnitude wise, because the induced EMF at this is maybe 5 volts, and here maybe I would say negative 8. Okay, so in terms of your EMF, your EMF induced, magnitude of your EMF induced is greater at point C. Why is that so? Because the speed is greater. Since you are like in the acceleration of free fall, right, you are going faster and faster. That's why when your speed of magnet comes up at a greater speed, the induced EMF will be greater also. Alright, so just think of these 3 particular points. Right? Okay, so yeah, so when the magnet exits the coil at higher speed, the induced EMF, there will be a induced EMF current flowing in the clockwise direction, and the magnitude of your EMF will be higher. Okay, alright, so yeah, so this is for your EMF.